Okay, this is a slightly tricky problem. There's a few bits and pieces that we need to go through in this question, particularly part B. Part B is a little tricky, so we'll look at that question in a minute. I'm going to work the whole question, starting from part A, B and C. So I'm going to remove that large version, we'll just quickly read through it. John weaves cloth by hand. Emma believes that faults are randomly distributed in John's cloth at a rate of more than 4 meters per 50 meters of cloth. Check her belief. Emma takes a random sample of 100 meters of cloth and finds she contains 14 faults. So we need to think through what sort of distribution is it. Well, we believe they're completely randomly distributed. They're one piece of cloth. If it has an error, we're not saying that it's going to have caused a snag that will cause it to happen again, so they're independent. The error is in terms of a distance. It's a rate question, so there's 4 per 50 meters of cloth. So that means we're going to be working with a Poisson problem, and we need to do a hypothesis test on a Poisson. That's the key information from that first part. So let's read that bit and go through. Oops, sorry. So I'm not working from that, I'm working from my own notes. So first part we need to make a note on is what are our key values going through. So we're going to start off with making a declaration of our variable. So x with L is the number of errors in L meters of cloth. Like we said before, they are random, independent, because we're not going to say that a tear could cause another tear. Potentially there is unlimited, so it's not about a binomial. We could actually have an infinite number of errors in a meter. So this actually leads me to believe that this XL is a Poisson with some lambda based on L, that length. We're actually stating in the question, we get told that lambda for 50 meters is 4. So that's 4 errors in a distance, but we're going to be testing 100 meters. So the lambda for 100 meters is 8 errors is the expectation. That's what on average we should be receiving. We're trying to make sure that 14 faults is not in this 5% significance level. So we're trying to check the top end. We've got 14 here. Is that in the critical region? And that critical region is 5% of values. Samples of 100 meters. Okay, so that's what we're looking at. Our hypothesis is, the null hypothesis is saying the lambda is 8. If we think the alternative hypothesis, if that lambda was less, that wouldn't be a problem to us. But if the lambda is bigger, that's where we're going to get a problem. So we're going to do a one-way tail test where lambda is greater than 8. That's where we get the marks for the stating the hypothesis. So remember this 14, it could be that side, could be that side. What we've got to check is if that 14 or more is in the region of 5%. So we need the probability of x for 100 being more than or equal to 14. A lot of people will just put in equal to 14. 15 would be worse. 16 would be worse. It would be a situation we don't want. Calculate our values. So we do 1 minus the probability of x 100 less than 14. Remember, it's a discrete distribution, so less than 14 is equivalent to less than or equal to 13. And we need to look at these values, and I can find those if I go back to my table. And in the tables, I've found them. There's my table, formula booklet. This is the Poisson tables. Lambda we're looking for is 8. and the x value is 13, saying 13 or less, so that's 9658. So 1 minus 0.9658, which gives me 0.0342, or 3.42%. 3.42% is in the critical region, therefore would actually lead to an error. So this 3.42 is in the critical region, which I forgot to note on my diagram. This is the critical region. So 3.42% in the critical region. If it's in the critical region, there is evidence to reject H0. In favour of H1, which this is the part people often miss out. They forget to say the section that what does this say? Because they said test her hypothesis. So Emma believes that the faults randomly distributed in John's cloth are they at 4.5. So there's evidence there to reject H0. No, the evidence is Emma is incorrect. The suggestion is that there are more errors. I'm giving in the question. Oh, sorry. She believes that the rate is more, not that it is. Suggests more errors. So she's correct. So I'm going to. So just being able to say evidence to reject H0, because we've been asked to look at Emma's belief, we've got to actually talk about Emma. So Emma is correct. It suggests there is more errors. And the next part is the one I'm expecting more problems with. So section B, Amani also weaves cloth by hand. He knows that the faults are randomly distributed in this cloth at a rate of lambda is 4 in 50. So lambda in 50 meters is 4, and we know that's to be true. He knows that the faults, so I really ought to declare a new variable for this, say y for L, and YL is the faults in a different person. Amani's sheets. The first part was dealing with John for L meters. So my X above was for John. So I'll just add that note on the top. So scrolling in, lambda is now 50. And Emma decides to buy a large amount of Amani's cloth to sell in pieces L meters long. She chooses L, so the probability of no faults is exactly 0.9. This is where the problem people get with this is trying to work out exactly how this structure works. And what we have to think is, in 50 meters we've got 4 errors. So we need to work out how many errors would we be looking for in L meters. So if there's 4 in 50 pieces, we've got 4 errors in the proportion of the length divided by 50. So that will give me my lambda for calculating the length needed. So now we have YL is a Poisson distribution with 4L over 50. Now, the chosen situation is where she's chosen it, so YL equals 0 is equal to 0.9. And we go to the formula booklet and we write down their formula, which is e to the minus lambda x over x factorial, and x in this case is 0. So these two terms completely disappear. So we now have 0.9 is equal to e to the minus 4 over 50 L. If I take the logs of both sides, I get the natural log ln, or log e, 0.9 is equal to minus 4 over 50 L. And if I go to the calculator and pull that up, calculator handy, no, I need to pull it up. I can rearrange this so that L equals minus 50 over 4 times log 0.9, or ln 0.9. I was about to write the log base e. I know I'm teaching you to suck eggs with that, but let's check. So I have negative 50 divided by 4 multiplied by the natural log of 0.9, giving me an answer of 1.317 equals 1.317, which to a suitable accuracy L is approximately 1.3 meters. Okay, and that's the suitable accuracy requested in 2 significant figures. Emma sells 5,000 of these pieces of cloth. She makes a profit of 250 on each piece that does not contain faults, but loses 50 pence on a piece that contains at least one fault. So this is about profit, so we don't need to know the costs. If she's selling 5,000, she's chosen the value so that the pieces of cloth with no errors, so no faults, the number of pieces we're going to have is 5,000 times 0.9. That's what the probability actually means. Is if you have a big sample, what proportion are you expecting to meet the requirement of having no faults? And that's 4,500. So we've got 4,500 at a profit of 250. With a fault, she's getting 5,000. 0.1 of those is now comes in as being a problem, and that's 500 minus 0.50. So we can multiply through. So the total in the end should be 4,500 by 2.5. Oops, so I didn't mean to pull up the whole screen. So 4,500 multiplied by 2.5 minus 500 times 0.5. And answer is £11,000. So total profit is £11,000. Okay, that's the full question done.